Assalamu alaikum students. We will learn about laws of thermodynamics today. First, we will study first law of thermodynamics with the help of heat and work, and then we will study a few special cases for first law of thermodynamics. After that, entropy and second law of thermodynamics, in which we will study irreversible processes, change in entropy, second law of thermodynamics, and Carnot engine. Let us consider this special type of container, which is a cylinder filled in with a gas and a movable piston. So it is insulated, its walls are insulated and its piston is also insulated, means that no heat can flow into or out of this cylinder from these walls or through the piston, but it is placed on top of a thermal reservoir. You can consider it as an electric stove whose temperature can be controlled with the help of this small knob. So this cylinder is placed on top of this thermal reservoir so that heat can transfer into or out of this system or the gas through this thermal reservoir only, because walls and piston are insulated. They are made up of insulating material, so heat cannot flow through these walls or piston, can only flow through the base which is placed on a thermal reservoir. And on the top of a piston, the piston has an area A, and on top of piston we have placed a container of lead shot in order to exert some external pressure on this system or the gas. So we can increase the number of lead shot or we can decrease from it in order to change the value of pressure that we want to exert on the system. At the current stage, let us consider that the volume of this gas is Vi, or the initial state volume, and the pressure that is being exerted on it is Pi, and this piston is not moving because the pressure of the gas inside this cylinder has balanced the pressure exerted by the lead shot. So both pressures are equal and the piston is balanced. So the pressure in the gas or of the pressure of the system is Pi, the initial state pressure, and volume is Vi, and we can consider that the temperature at this stage is Ti, the initial temperature, that can also change during the transition, and we can plot it on a PV or pressure volume diagram like this one. This is a graph. Y-axis has pressure value and x-axis has volume values. So the initial state of this system can be plotted on it like this. This is I is the initial state that has a volume of Vi, pressure of Pi, and a temperature Ti. Now let us try to change this initial state of a system. When we change this, when there is an involvement of heat, because heat may or may not transfer from or through this from or to the system is this gas inside. We call such a process a thermodynamic process, in which we change from one state to another state. Now let us reduce some of the lead shot so that the pressure on the piston is decreased. What will happen then? Of course, when the pressure is reduced on this piston, the gas inside will push it upwards like this. So we removed some of the lead shot and the piston is moved upward by the gas here by a displacement of S. So we call this distance that is traveled by the piston as a result of the force exerted by the gas underneath this piston as S. And as you see, the volume has expanded as a result of decrease in pressure here. So means that our pressure is reduced, but our volume of the gas has increased. Now we consider this as a final state and try plotting it on the PV diagram like this. The pressure is reduced from this level to this level, and volume has increased from this level to this level, and we call this pressure as PF, or the final pressure. Volume is Vf, and let us consider the temperature is changed from Ti to another value Tf. And during this process, during this thermodynamic process, while changing the state from I to F, the work done is positive. The work done by the system is positive. The system is a gas that has expanded, the volume has increased, and it, as a result of this volume expansion, the gas has moved the piston upwards. It has done a positive work on its surroundings. Now we can change from our final state back to the initial state, means that we can compress the gas and increase the pressure. We increase the lead shot again, and it will move the piston back again by the same amount. Now our system has transited from the transitioned from the final state back to the initial state, and the work done during that is negative. Work done by the system is negative, because the work is done by the surrounding in on the system and compress the gas. The volume is reduced as a result of this work done, therefore the work is considered to be negative. This work done is negative. The work which is done by the system, that is negative, okay, but not by the environment. So we are considering only the work done by the system. Okay, between these two states, initial and final states, there are many different ways in which we can bring our system from one state to another one, which may or may not involve the transfer of heat between the system and the thermal reservoir. So in the previous case, we observed a path to go from initial state to a final state without any involvement of heat energy transfer. Now let us take a look another way of bringing our system system from initial state to a final state. Now let us bring our system from initial state to final state using through a different thermodynamic path. But first we have to note that the final state has larger volume than the initial state, but smaller pressure than the initial state. So first let's keep the pressure constant, and we keep it constant by keeping the load on the piston unchanged. Then how we can expand the gas to increase its volume? We can do so by increasing the temperature of thermal reservoir by turning this knob. We turn this knob, increase the temperature. By increasing the temperature, the heat flows from thermal reservoir to the system, and as a result it exerts more pressure on the piston and push it upwards and expand. As an expansion, of course, you know that the volume increases. So the heat flows into the system, it causes it, and system goes from initial state to an intermediate state, we call it A, and in moving from this state to this state during this path, and the transition, the volume has increased from this value to this value here, but the pressure has remained constant. Okay, now we want to bring it to this state. So we have already achieved this volume. Now we want to decrease the pressure, but of course we do not want to change the volume because we are already at the final state. So we have to reduce the pressure. How we can reduce the pressure of the system? We turn the knob again. We turn the knob again to decrease the temperature. When the temperature of the thermal reservoir is decreased, the heat will flow from system to the thermal reservoir and the pressure will decrease, but we do not want to decrease the volume, right? So we fix the piston at its position, we wedge it, we lock the piston here, so the volume of the gas does not change, because you know that the gas fills up the volume of the container. If it is smaller or larger, does not matter, it will fill up the whole volume. So the pressure of the gas can be reduced by taking the heat out of it. So the thermal energy will be transferred from the system to the thermal reservoir and the pressure inside it will decrease, but the volume will not decrease because we have fixed the piston at its position. Now we have decreased the temperature, the heat is flowing downwards from the system to the thermal reservoir, and we will volume does not change, the piston does not move, but the pressure decreases to a new state, a new value, and that value is our corresponding to our final state that we want. So in this, the overall work done is positive. Why? While moving from state I to an intermediate state A, the gas or the system performed work in moving the piston upwards by expansion. So the gas expanded, it pushed the piston upwards and the work done was positive. But while going from the intermediate state A to a final state F, there was no work done. So the work done was 0 during this process because the piston did not move. So the system did not do any work during this transition. So the net work done was positive. Now let us find out how we can calculate the work done during each thermodynamic process. Let us consider the piston is moved up by a small displacement ds, during which the force exerted by the system remains constant, because you know that the formula for work done applies to constant force only. So if the force is changed, it is variable, we have to find out the work done for the small patches during which the force remains constant and then take an overall sum. So the small work done during the small displacement of this piston ds is represented as dw. This is the work done during which the force remained constant, with very small portion of it. So the work done can be represented by F dot ds, as you know that F is the force is equal to, in terms of pressure we can write it like this, because pressure is equal to force per unit area. So force can be represented as pressure times area, and ds is written like this because this is a dot product and it will be equal to F times ds times cos of theta. So the theta is 0 because force and the displacement, when it was the gas was pushing from the bottom and the piston was moving upwards, both were in the same direction, means the angle was 0 and cos of 0 is 1. Therefore F dot ds will be equal to F times ds times 1, right? So F is replaced with pressure times area, and this is like this. So why we did that? We can rearrange the terms now. A, we combine it ds, Why? Because A is an area, ds is a length. So, area times length makes volume, right. So, pressure times volume. So, the work done can be represented as P times dV. This is a very small differential volume during our dW work done, this one. So, how we can calculate the total work done during the whole process or during the whole thermodynamic process of changing the system from moving the system from initial state to its final state. We have to perform integration like we did before while calculating the work done by variable force. So, the total work done will be equal to integration of dW, which will be equal to the integration between the limits initial volume to final volume of d of P dV. P is the pressure, dV is the volume. Okay, now let us see how the work done will how we can calculate work done for different processes, different type of thermodynamic process in which we follow various different paths, because from in moving from initial state to final state there can be infinite number of paths that we can follow. First one, the one that you saw in the first example. So, we moved initial to a final state and the work done was positive. This highlighted region, this orange highlighted region is actually the total work done. Why? Because you know that this integration of the curve represent is actually the area underneath this curve. So, we can say that the area under the curve is equal to the work done during that process. Now, let us see another one, the one that we saw in our second example. The initial state was moved from to an intermediate state, and from intermediate state we went to a final state, and during this the straight line the pressure was remained kept constant, and for the second A to F our volume remained constant. And during this process, because there was no compression involved, all the work done was by the gas or by the system on the piston in while expansion. So, the work done was positive, and the value of the work done will be the area under this curve. Now, you can see that this work done is different than this work done, but we have the same initial and final states. Our initial and final states are same, but because of the different path followed to go from initial state to final state, the amount of work done has been changed. So, this was using this path, the work done was lesser as compared to in this case. Now, there is another way we can use. We go from I to another intermediate state by keeping the volume constant, and then we move from this intermediate state to a final state here. So, the area under the curve is highlighted with this orange color. The work done is positive because there is no compression involved, no work done on the system, but work is done by the system in moving from this state to the final state, because this is the increase in volume. You can see the volume is increasing from here to here. This is the expansion, the work done as a result of expansion of the gas. So, the work done is by the system, that is why it is positive, but the amount of work done if we follow this path is much smaller than either of the first two, right. Now, we see another path now. Okay, so these three examples of different paths followed, but to go from same initial state to a same final state, we can say that the heat and work are path dependent quantities. So during this path there was no heat transfer between thermal reservoir and the system, but here there was, and here there was also amount of heat transfer between the system and the thermal reservoir. So the amount of that work done and heat transfer all are dependent on the path, which path we follow. Therefore we can say that heat and work done both are the quantities that depend on the path we choose to bring our system from initial state to final state. See another one. In this, the initial state is this and final state these are the same as before, but this green line represents one path and this red line represents another path. You can notice that first we are going from this to G, from G to an H state, H to the final one F, and the another one from I to C, C to D, and D to F. Now if you want to calculate the work done for both, because it is the area under the curve, if you look at the area under the curve between this green curve, it is a lot more than the area under the curve of this one, the area under this red curve. The area under red curve is only this one, this small portion, but the area under the green curve is all of this one, right. So this path has means if you want to follow this path, we will have to do a lot of work in order to go from initial state to final state, but if you follow this path, we will have to do very little value of work to go from initial state to final state. Or in this path, when we are going from final state back to initial state, a compression is involved because the volume is decreased from this value to this value. Okay, so this is the actually in this case, because we are compressing the gas, the work is done on the system. We increase the load, we increase the pressure from here to here, right. So this is the pressure from this is the pressure level, final one, and this one is the initial one, and we are going back from final to the initial one. So the pressure is increased, that compressed the gas means that the work is done on the system. Therefore the work done is considered negative, because we always consider the work done by the system. So it is done against it, therefore the work done is negative, but the value of work done will still remain the area under the curve, because the work done is on the system, that is why it is negative. Now let us see this one. This is different. This is thermodynamic cycle, means first we go from initial state to final state and from final state to initial state, right. So we follow this path in going from initial state to final state and back from final to initial. This one, this makes a loop, right. So the work done will be equal to the difference of the work done between these two processes. First we go from initial to final state, the work done will be the total area under this curve, all the highlighted one from here, all from the horizontal axis. So all the area from this curve to the horizontal axis will be the work done while moving from I to F, and the work done while moving from F to I will be under this curve, okay, to the horizontal axis. Now you can simply see that this one, the area under this curve I to F, is this highlighted portion larger than the area under this curve, and also the work done during this process going from I to F will be positive, and the work done from in going from F back to I will be negative, because I to F is the involves the expansion, right. So first it is the volume, and in the final one this is the volume. So the volume has increased, means that expansion has caused, and the work done is by the system, that is why it is positive, and while going from I to F, this one from F to I, like this one, the gas has compressed from this state to this state, means that the work done by the system will be negative. Okay. So, the net work done will be this highlighted portion, the area between the loop. Now, the first law of thermodynamics can be expressed with the help of this formula. Here delta EINT is the change in internal energy of the system, and this one is the internal energy of the system at final state. This is the internal energy of the system at an initial state, which is equal to the heat energy supplied to the system minus the work done by the system. Okay. So, we can say that the heat energy supplied to the system minus the work done means that when an energy is supplied to the system and the system does work, the leftover energy, means some of the energy will be converted into work, and the leftover energy will cause a change in the internal energy of the system. Now, the first special case of the first law of thermodynamics is an adiabatic process. In adiabatic process, we change the state of a system without any heat transfer. So, the process that occurs so rapidly or occurs in a system that is so well insulated that no transfer of energy as heat occurs between the system and its environment. You notice that earlier we had a thermal reservoir at the bottom, now we have another insulating block at the bottom. Now, heat energy cannot even transfer from the base. Walls were already insulated, so heat energy cannot transfer from anywhere into the system. Therefore, the change in internal energy is equal to minus W. Why? Because change in internal energy was equal to Q minus W. Q is the heat transfer to the system, that is 0. Therefore, 0 minus W will be minus W. Okay, and the second is constant volume process, a process in which the volume of the system is kept unchanged. So, we fix the piston here and we do not let it change, then the system will perform no work. The work done will be 0. Okay. So, neither the work will be done on the system or by the system, then it will be equal to 0. So, Q minus 0 will be equal to Q. This was for the cyclic process. Now, a free expansion process. So, these free expansion processes actually are adiabatic processes. In adiabatic processes means that no transfer of heat takes place between system and its environment, and no work is done on or by the system during this expansion. Therefore, Q is equal to W, means no heat is transferred to the system or from the system, and no work is done on the system or by the system. So, both are equal to 0. Therefore, the change in internal energy will be equal to 0. It can be expressed through this free expansion process. There is a stopcock here. So, we can open this stopcock and the gas can expand from here to this vacuumed portion. There is no gas here, it is totally empty from here. So, the gas will move, means that the gas is expanding, its volume is increasing, it is expanding freely, and the container is all insulated, means that there is no way heat can transfer to the system or from the system. Therefore, this is a free expansion process, on its own, because if the heat is transferred to the system, it can cause it to expand, right? It can force it to expand by increasing its internal energy. But in such a process, the free expansion process, no heat energy transfer is involved, therefore no work is done also, and therefore the internal energy, the change in internal energy is 0 for a free expansion process. Okay, now irreversible processes. So as the name suggests, these are not reversible, means that they are only one way processes and cannot be reversed. For example, broken egg, cooked food, you cannot uncook a food, and the waves eroding a sandy beach. So these are some examples from our daily life which are irreversible processes. A broken egg cannot be placed back into its shell and bring it back to its original state, and cooked food cannot be uncooked. Okay, the direction of these irreversible processes is not actually set by the change in internal energy, but it is set by the change in entropy. Entropy is represented with S, and the change in entropy is represented with delta S. Okay, what is entropy? It is actually defined as the degree of disorderness of a system. So the entropy postulate states that if an irreversible process occurs in a closed system is a system that is not influenced by the external factors. So the irreversible process occurs in a closed system, the entropy S of the system will always increase, it never decreases. So the system, the entropy always increases, and in terms of irreversible process, if we want to bring it back to the original state, we have to reduce its entropy, which is not possible. Now change in different ways. One is in terms of heat energy that is transferred to or from the system, and another one is in terms of the degree of orderness or the arrangement of atoms and molecules. Now the change in entropy can be expressed mathematically by this formula. If SF is the entropy of the system at final state, Si is entropy of the system at initial state, then change in entropy will be equal to the difference between these two entropies, and it will be equal to dq, which is the transfer of heat energy from or to the system, and T is the temperature in kelvins at which this heat transfer has taken place. From this formula, we see that the change in entropy depends only on two quantities, which are dq, or the heat energy transferred to or from the system, and the temperature at which this transfer has taken place. Now let us consider a reversible process. Reversible process is the one which can restore its initial state, means that such a system that goes from initial state to final state, and from final state back to initial state. And here new term you will see, isothermal reversible process. So reversible process you already know, the one that can be reversed to its initial state, and isothermal is the one in which the temperature of the system does not change. Okay. So this is such a reversible process in which the temperature of the system maintains. Now let us consider this state is the initial state at which the pressure is Pi, the volume of this gas or the system is Vi, and the temperature is T. this system, the cylinder is again it has insulating walls. It does not let any heat flow through the walls or the piston. The only way it transfers heat to or from the system is through the base with the help of thermal reservoir. So, we change from initial state to this final state, which is the expanded state of the system, means it will increase the volume. But we also know that this isothermal means the temperature should not change, and you know that when the gas expands on itself, its temperature reduces. So, we reduce the lead shot to decrease the pressure on the piston. When we do that, when we do so, we let the gas expand. So, we reduce the lead shots to a certain value as we like, then we let the gas expand on its own. When it does so, its temperature decrease, and in order to maintain the temperature, heat is provided from the bottom or from the thermal reservoir to maintain the temperature. And at the final stage, the pressure is P f, volume is V f, and temperature is T. Notice that the temperature is not changed, P I to P f, V I to V f, but T remains the same. Now, we can draw a curve like this. We have moved from initial to the final state through this path, and this path, on this path the temperature has not changed. So, we write it here that T is constant, T does not change, and we name this curve during which the system goes from initial state to final state at a constant temperature. Process of going from initial state to final state without any change in the temperature is called as isothermal process, and this graph or this curve is called as isotherm. Now, we know that the path between initial and final states, we can perform integration to calculate the change in entropy, because this is change in entropy is calculated by taking by performing integration on dq over t. We know the value of T, and we also know the value of heat transferred from the bottom to the gas. We can perform integration and calculate the change in entropy. So, since the T was constant, therefore, we do not need to keep it after the integration sign. We can bring it outside the integral and I initial state to I final state and change in the the transfer of heat. Therefore, since it is from initial to the final state of dq, means that the total heat energy transferred during the process, during this isothermal process, and we can write it like this: the heat energy transfer divided by the temperature at which this heat transfer has taken place. In order to find out the entropy change for an irreversible process occurring in a closed system, replace that process with a reversible process that connects the same initial and final states. This is actually for the reversible process, but if we are dealing with irreversible process, we can have same initial and final state values, this and this, and use this formula for that, because initial and final states are independent of the path taken. Now, the force due to entropy. Let us try to understand with the help of an example. We find out why the rubber resists the stretching. It is also it involves the entropy in it. You know, the rubber band, when you try to stretch it, it resists, right? You have to apply force to stretch it. According to first law of thermodynamics, dE, or the change in internal energy, is equal to dQ, which is the heat transferred from or to the system minus the work done, right. The work done by the rubber band while being stretched to a small length, dx, can be written like this. So, when we are pulling it, the work done by the rubber band will be equal to this. We have pulled it, but this formula is for the work done by the rubber band, because the work is being done on the rubber band, which is a system now. Instead of gas, we have a rubber band as a system. So, the work done is on the system, therefore, the work done by the system will be negative. So, F is the force applied, and that small tiny distance during which this force is applied is dx. And for small changes, we have considered that during this change there is no change in temperature has taken place, because that is very small length, but during that the force has a constant value. And for small changes in change in the internal energy, change in the heat energy transfer to and from the system, and the entropy during isothermal process. Isothermal means temperature does not change. Since we assume here that we have stretched it very little, so that the temperature has still the same value, it does not change, means it is an isothermal process, and for that we can use this formula, ds is equal to dq over T. Now, from this equation, dq is equal to dE minus dW, right, and from here that dW can be replaced with minus f dx, means minus times minus, it becomes plus, and we can write it like this, because dq is equal to TdS, we put this value here and the value of dW here, we get dE is equal to TdS from here, because dq is equal to, when t goes there and multiplies the ds, TdS plus f dx. Now, for a very small stretch in the rubber band, so that the total change in internal energy is 0, means that the change in internal energy is 0. We have stretched rubber band very little. In that case, the change in internal energy will be 0. We replace it with 0 and we will get this formula. From here we can find out the value of f here. So, f will be equal to minus T times ds over dx, and this is the formula for the force due to entropy. It can be observed. Now, it can be visualized through the example that we consider of a stretching of a rubber band. That this is a patch, this is a patch of the rubber band in the normal state, and in the normal state the molecular chains, the polymer chains are coiled like this. So, when we apply force and we stretch it, these becomes uncoiled, these coiled polymer chains becomes uncoiled like this. Since we know that this is the higher degree of disorderness, right. So, means that this is higher entropy, and this is better degree of disorderness, that these are arranged in a better way. There is less disorderness in this arrangement when we stretch it, means that this state has less entropy when we apply the force, and when we release it, it immediately goes back. Therefore, the force and the entropy has a negative sign in it. So, by applying the force, the change in the entropy is negative. Now, the second law of thermodynamics, it is also called as the law of entropy. It states that if a process occurs in a closed system, the entropy of the system increases, but for irreversible process, and remains constant for reversible process, it never decreases. It says that the entropy of a system either remains constant or it increases. It increases for irreversible processes and it remains constant or unchanged for reversible process. Means that it never decreases, it either increases or remains constant. Mathematically it can be represented like this, that delta S is either equal to or greater than 0. This is the mathematical relation for second law of thermodynamics. Carnot engine operates on the principle of Carnot cycle, which is named after the French scientist and engineer who proposed this cycle. His name was Nicolas Leonard Sadi Carnot. And this is an ideal heat engine. It operates between two temperature reservoirs. One is high temperature reservoir, another one is low temperature reservoir. It absorbs some heat from the high temperature reservoir, and there is a working substance, can be a gas, that converts some of this absorbed heat into useful work, and that work means expansion of gas is called can be considered as work performed, because expansion pushes the piston upwards, like you saw in the previous examples that we discussed in earlier slides. So gas expands and perform work. So that working substance performs some work here, and rest of the energy is released to low temperature reservoir. Now let's take a deeper look at the performance of Carnot engine with the help of its. Now let's take a closer look at the working of Carnot engine with the help of its PV diagram. Now consider that the system was at this state initially, the state A, where the volume is this one, we call it VA, and the pressure is this one, we call it PA. And at this state, this system or this working substance gas here, it absorbs some heat energy QH from the high temperature reservoir here, and this is the gas then expands from A to B. Now its volume is here. This is a new state. Now this is the volume and this is the pressure, and during this expansion, as the gas was expanding, it absorbed some heat from the high temperature reservoir in order to maintain the temperature. So the temperature is maintained at this TH during this process, and the expansion has taken place. So you know that when a process is occurring at without any change in temperature, that is called as isothermal process, and during this isothermal process, heat is absorbed in order to maintain the temperature at TH. Now the gas expands further and the pressure is reduced and the gas is expanding. So this is the value of pressure now at state B, and when it further expands under lower pressure, this was the means the pressure was decreased, this was the new value of the pressure, and gas has expanded without any transfer of heat. And you know that when the gas expands, its temperature reduces. So when the gas is expanding from B to this state, and we call that we consider that at this state the volume was VC, corresponding to this new state. So volume of the gas at B was this here, from the x-axis we can see, and on the new one it is here. So means that gas has expanded from here to this value, right, but without any transfer of heat, without absorbing any heat. Means that if it is expanding without any absorption of heat, its temperature will drop. Now this temperature has dropped from TH to a new value TL, because it is in contact with TL also. It cannot go below this because they are also in thermal contact with this. Now when it arrives here, this process has taken place from moving from going from state B to state C without any transfer of heat. And you know this process is called as adiabatic process. During these two processes from A to B and from B to C, the gas has expanded. So gas expansion means positive work, right? So during these two processes, the work done is by the system, and hence the work done is positive. You can just memorize it in this way, that when the gas expands, the work done is positive. When the gas is compressed, the work done is negative. Now from here, see, we start to bring our system back to the initial state. So first, and also remember that since the gas is being compressed, the work done should be negative. And after this point, the pressure is further increased very fast and significantly to this value, but during this process we have not allowed any transfer of heat to take place. So the volume has been decreased from here to this value, and the pressure means from here to almost here, this one on the x-axis. A small change in volume has taken place and a large change in pressure has taken place. So the volume is decreased and pressure is increased, but no transfer of heat has taken place during this process, in going from D to A. Since it is a compression, again the gas is being compressed, the volume is decreased, then work done during this process should also be negative. So work done in moving from C to D and D to A is negative, and since there is no transfer of heat during this process in going from D to A, it should be an adiabatic process. Now just look at it, because this is one graph, this is the same graph, only this is separated for these two, for first two states and for last two states. This is for first and second, A to B, B to C, and this is from C to D and D to A. Now if we want to revise it, it is very simple. First we go from state A to state B through an isothermal process, and heat is absorbed from high temperature reservoir into the system, and then we go from state B to state C without any transfer of heat, but the temperature is decreased to a lower value. Now this process is called as adiabatic process, and expansion of gas has occurred during this process. So in both processes from A to B and B to C, the gas has expanded, therefore the work done is positive. Now going back from here, the gas is compressed under a higher pressure, the temperature increases, but the excess heat is transferred to low temperature reservoir, and the temperature is maintained at TL. Since the gas is compressed, the temperature will be negative, but the temperature is maintained. Since the gas is compressed, the work done is negative and the temperature is maintained, therefore this process is an isothermal process. After that, the system has moved from this state D to state A, and during this time no heat transfer is allowed, no heat transfer has taken place, therefore the system is adiabatic, the process is adiabatic process, and the work done is negative because the gas is compressed. Carnot cycle can be plotted on temperature entropy curve like this. So during the process of moving from state A to state B, we can observe it in a better way having both graphs together. Here this is the Carnot cycle is plotted on energy and temperature entropy diagram. This is temperature and this is on the x-axis is entropy. So during the process of going from A to B, here the heat was absorbed, temperature was maintained along this black line. It relates to the vertical axis here. So this temperature is kept constant, but entropy is increased from here to this value, from here to this value, and heat was absorbed. So you know that when the heat is absorbed, the entropy increases. And when the system goes from B to state C, there is change in temperature from TH to TL, right? But there is no change in entropy because there was no transfer of heat to or from the system took place during this process. This was adiabatic process. This was isothermal process. Now again another isothermal process takes place and system goes from C to D, but during this process the heat was released from the system to the low temperature reservoir. That is why the entropy has decreased from C while going from C to D. The entropy has decreased because the energy left the system. And from D to A, again there is no transfer of heat energy involved in this process. This is adiabatic process, therefore there is no change in entropy at all, and the system goes back to its initial state. Now the work done by Carnot engine is by, according to the second law of thermodynamics, we can write this formula: W is equal to QH minus QL, the heat energy absorbed minus the heat energy rejected. It must be equal to the work done. And the entropy change during one cycle is represented like this. So this is the change in entropy of the final state, and this is the change in entropy in the this is the change in entropy of the high temperature reservoir. This is change in entropy of the low temperature reservoir. So this is the heat which was absorbed or left the heat temperature reservoir at this temperature. You remember that entropy is equal to the transfer of heat divided by the temperature at which that transfer of heat has taken place, minus QL divided by TL. This is the energy that was released from the system to the temperature reservoir, low temperature reservoir. Therefore we can write it like this: since for a complete Carnot cycle delta S naught, so delta S is equal to 0. That is why this one is equal, because you remember from the previous graph we start from A and go back to A. The entropy also comes back to its initial state, therefore the change will be equal to 0 because it has come back to its original value. Therefore if it is 0, so delta as QH over TH minus QL over TL will be equal to 0. Therefore we can write that QH over TH is equal to QL over TL. This is the change in entropy during one cycle of the Carnot engine, right? Now the efficiency of Carnot engine is written as this. So this epsilon represents the efficiency. It must be equal to the energy we get, means that the actual work that we have got divided by the energy we pay for, means that the energy which was imported or absorbed from the high temperature reservoir. So the work done, the energy we get is the work done, and the energy we pay for is actually this energy that was absorbed from the high temperature reservoir. So this is the efficiency. It can be written like this because W from the second law of thermodynamics is expressed like this, and this is the QH as it is. So we can write it like this also: 1 minus QL over QH, and this is the efficiency of Carnot engine, because QL here is the heat energy and QH is also the heat energy, and both of them are equal by this equation for one cycle. So QH over QL will be equal to TH over TL, and therefore we can write it like this. Okay, I hope you understand it. Now, how a perfect engine will look like, and a perfect engine will be an engine that has an efficiency of 100%. A perfect engine will be the one that does not release any energy or heat energy to low temperature reservoir. In fact, it converts all the energy which was absorbed from the high temperature reservoir into work. So the energy which was absorbed is all of it has been used to perform useful work, and none of the part of that energy is released or wasted to low temperature reservoir. That's all for now. If you have any question, you can discuss with me later on Kaizala or our next live session. So after that we will do some numerical problems related to the topics we have studied in this lecture.